and the paper is by Anupam Gupta, Amit Kumar, and Dipmalya Panigrahi, and Dipmalya will give the talk. I think
Am I audible?
Yes.
Great. Are my slides visible?
Yes.
Perfect. So thanks, Christian. I'm Dipmalya Panigrahi. I'm from Duke, and I'm going to talk about caching with time windows, which is joint work with Anupam Gupta from CMU and Amit Kumar from IIT Delhi. So let's dive straight to the problem. We all know of the caching problem. I have a disk which contains n pages, and I have a cache that can only hold k of those pages at any time. K is much smaller than n. I get a sequence of page requests, and I need to satisfy those requests by bringing the corresponding pages to the cache, if the page is not already there. In the weighted version of this problem, the cost that I incur is the total sum of weights of all the pages that I need to evict in order to create enough space to serve all the requests. Now, in the caching with time windows problem, the only difference is that now every request also comes with a deadline, which is in the future. And you don't need to satisfy the request immediately, but you need to satisfy it at some point within the deadline. So let's see a simple example. So let's say here's my timeline, and imagine that I have a cache of size 1 that holds some page P2. So let's say I get a request at T1 for a page P1, and the request specifies a deadline of T5. So that means I need to satisfy this request within time T5. So maybe I don't satisfy it immediately. Page P2 remains in the cache. I get another request at time T2, this time for page P2 itself, and has to be satisfied within time T4. Of course, I keep P2 in the cache, it immediately satisfies the request. I get yet another request at time T3 for page P1 again, and this has to be satisfied within time T6. Now remember that I have this waiting request from time T1 that I still haven't satisfied for page P1. So maybe at this point, I decide that I need to satisfy both these requests. So what I do is I swap in page P1 into the cache, and I swap out page P2, and the cost I incur in this swap is the weight of page P2. Okay, so, and as is usual, we would want to minimize the total sum of weights of all pages that we swap out during the entire schedule. So what's known about this problem? So first, it's obvious that if all these time windows are of length 0, which means that the deadlines are precisely when the requests are being generated, then this is exactly the standard caching problem, for which we know that the best deterministic competitive ratio is theta of k, and the best randomized competitive ratio is theta of log k. For caching with time windows, the same results hold for the unweighted case. In fact, if all the page weights are 1, then there's an easy reduction to standard caching, and it loses only constants. But in the weighted case, when pages have non-uniform weights, all that was known previous to our work was a paper that I wrote with some other people a few years back that gave a theta k deterministic algorithm for this problem. So that matches up to constants the best result that we have for the special case of standard caching. And what was open is to obtain a randomized algorithm that does better than this deterministic algorithm. And to just give you a sense of where the problem becomes difficult, imagine that you have just a single cache slot. Even in this case, which is extremely simple for standard caching, because you simply use that one cache slot to serve the request, the current request, it's not trivial at all in the case where you have time windows. So even with a single cache slot, it's not clear how to schedule your requests or how to schedule servicing your requests that would minimize cost. So our main result in this paper is to obtain a log k times log n competitive ratio randomized algorithm for weighted page caching with time windows. So it doesn't quite get to all the way to the log k that we would hope for, but it gets an exponential improvement, at least in cases where n is not too large. So in addition to this result, we have some other results in this paper. So we show that for the offline version of this problem, i.e. if all the requests are known up front, then the problem is NP hard, and in fact also APX hard, which is in contrast to weighted caching in the standard model, which is polynomial time solvable. And we complement this hardness result by giving a constant approximation offline algorithm for this problem. Now, from a technical perspective, there are two main contributions of this paper. The first is that we show the standard LP relaxation for weighted paging or weighted caching has an integrality gap of omega k for this problem. So we can't rely on the standard LP. So one of our main contributions is a new LP relaxation for the problem that we call the hitting set LP. And indeed, this is the first LP-based techniques that we know of for this emerging domain of online algorithms with delays or deadlines that this problem also belongs to. So I don't have time to go into the technical details of the result, but I'll give you a glimpse of two of the main challenges that we grapple with in this paper. So let's think of standard caching. So what I've shown here are a bunch of pages, and the crosses on those lines are the requests for those pages. So now if I'm at time t and I have a request for page P4, I can look back in time and look at the last request for every other page, form intervals as I have shown, these red intervals, and I can insist that at least n minus k evictions must have happened in these red intervals. And indeed, this is a complete description of the problem. So this allows us to think of standard caching in terms of just recording evictions, and you don't really need to care about page insertions because they happen on demand. Unfortunately, this is not true for caching with time windows. So here, along with these red intervals, we also have green intervals, which are the request intervals within which we have to serve a request. And whether a constraint of the form that I wrote for standard caching is true or not depends on when I decide to serve a page. In other words, when I decide to insert a page into the cache. So we have to explicitly track insertions, and that turns out to be really difficult. So that's one of the main challenges we deal with. The other main challenge comes from an example of the kind that I have showed here. Imagine that you have a very heavy page that has a lot of very short requests and a bunch of light pages that have requests aligned as shown. So how would I serve these requests? The right thing to do if I have a cache of size 1 would be to evict the heavy page just once and serve all the light requests by taking advantage of this eviction. But this loses out in terms of being able to piggyback on or amortize the cost for these light requests because maybe there are some future requests that I haven't seen. And so there is this constant tension we have to deal with of whether we serve a request early or we wait till we see other requests for the same page. So that's all I have. I'll just conclude. So we give this log n log k comparative ratio. It extends to more general versions, such as if you have delay penalties instead of fixed deadlines. It is open to whether we can get a log k comparative randomized algorithm is an open problem, although we don't know of any example for our algorithm that does worse than log k. Thank you, and I'll be happy to answer questions.
Thank you very much for the nice talk. Do we have any questions in the audience? I don't think so. Oh, there is. Let me just check how this works. Sorry. Yes.
Hi, I have a question. So I want to know whether or not like the log n log k competitive, where is the bottleneck come from? Is from the rounding part or on the solving fractionally part?
So both rounding and solving fractionally we can do in log k. The problem is the LP that we solve does not exactly give a schedule. So because of this thing that I mentioned where you can't really track page insertions, And since you can't give an exact schedule, we have to run an additional algorithm that transforms the LP solution into a valid schedule, and that transformation loses a login. I think David has a question. Do you think the login term is necessary? I don't think so. As I said, even for our algorithm, I don't know of an example where we lose that login, but our analysis seems to be losing it.
Okay, thank you very much. And I think we should move to the next talk. I just need to find the list again. Okay. Right. So, Sahil, are you giving?
Yes, Christian.
Okay, great. Can you already share your screen, or?
Sure, let me share the screen.
Can you try?
Yeah, can you see it?
Yes, okay, great. So our next talk is on online vector balancing and geometric discrepancy by Nikhil Bansal, Hao Tian Jiang, Sahil Singla, and Makran Sinha.
Thank you, Christian. Okay, so we get started. Yeah, so this is joint work with Nikhil and Makran from CW Amsterdam and Hao Tian Jiang from University of Washington on some online discrepancy problems. So let's first look at an offline simple problem, which we call offline interval balancing. Imagine you have a unit interval 0 to 1 and a bunch of points lying on it. So you know all the locations of these points. Your goal is to just assign them a plus or a minus color, such that every interval is nearly balanced. By that I mean, like, look max over every subinterval. Look at the number of pluses and the number of minuses, the difference, the magnitude. You want to minimize this. So that's the question. And I claim like this problem is very easy. I can just alternate. So starting from the leftmost end, I can go alternately plus minus. This will ensure that max over all these intervals, the discrepancy, this difference, is at most 1. So this is the offline version, simple. Now in this work, we are interested in the online versions of these problems. So what we call online interval discrepancy, where these points are falling inside this interval from a uniform distribution. So maybe x1 lands. As soon as it lands, you have to immediately color it plus or minus. And you cannot change your decision. The main difficulty comes because you don't know eventually x1 is going to be an odd point or an even point. So you cannot run the old strategy. And the old strategy was giving us discrepancy 1. I mean, what can we do here? Random coloring is usually pretty bad. So if t is the number of points which are arriving, so t will be the most important parameter in the STOC. So t is the number of points. Random coloring, just because of simple variance bounds, you'll lose omega square root t. Whereas offline, you were getting a constant. So the natural question is, can we get much smaller, like constant or polylog t's? And in case you're wondering, like for some adversarial models, it can be shown that, okay, you cannot do much. You have to lose the square root t. So that's why we make some stochastic assumptions. So our result for this problem in this paper is that we get a polylog bound. So we get a log cube t and a square root log t lower bound. So this is tied up to some polynomial factors. And there's a work of Jiang et al. Earlier from last year, which obtained some much bigger bounds. So we also studied generalizations of this problem. So you can generalize this problem to 2-dimensional or even higher dimensions. So the 2-dimensional problem, first the offline variant, which is known as offline Tusnadi's problem. You have again given these points, you want to balance every axis parallel rectangle. So again, for every axis parallel rectangle, number of pluses and minuses, you want them to be balanced. Now the problem is tricky offline already, but we know polylog results. But okay, the focus of this talk is the online variant of this problem. Like, what if these points are being sampled uniformly in this square? As soon as they land, you have to color them. Again, random coloring is bad. The question is, can we do much better polylogs? And yes, we do obtain this result. In d dimensionals, we get like log to the 2d plus 1. So for d equals 2, you get log to the 5. And again, like the results are tied up to polynomial factors. The way we obtain all these geometric results is actually by taking a linear algebraic view, which will lead us to like some vector balancing problems, which are already very interesting in themselves and have a long history. So let's look at first the offline vector balancing problem. So what's the offline vector balancing problem? Now I'm given t vectors. So rather than given t points, I'm now given t vectors in some n dimensions. Maybe you can just think of n being small, but I mean, other variants are also interested. And all these vectors have L infinity norm bounded by 1. Your goal is to color them plus or minus, such that every prefix is nearly balanced. So So what I mean, like for every prefix, the sign sum should have like a small infinity number. And this is the goal. And to see some intuition, like, okay, the one-dimensional version is very easy because I can just greedily color these scalars so as to ensure that this is less than or equal to 1. So even offline, however, this two-dimensional version becomes tricky. I mean, if you haven't seen it before, like one needs a little thought. And random coloring is always bad for all these problems because t is the number of points. I'll be losing omega square root t, whereas I want like very, very mild dependencies on t. So what's first known for this offline problem? So what's known offline is you can get actually even results independent of t. So it's a result of Barane and Greenberg. And you can like you can get better dependencies on n, but then you have mild dependencies on t. This is the Banashek's result, which was made constructive by Bansal and Kwan. And this is a very standard problem. It captures many, many classical discrepancy problems like Spencer's, Cohn-Lewis, Steinitz, and has many, many applications. But in this work, we are interested again in the online variant of these problems, which we were motivated by some applications in fair division. Like it captures some online NV minimization. So but there are other applications as well, like randomized control trials. So what's the setting? That you have these vectors arriving from some known distribution P. So it's a distribution over vectors at L infinity norm at most 1. So arrivals are IID. As soon as a vector comes, you have to immediately color plus or minus, and the goal is the same. You want every prefix sign sum to be small, this discrepancy to be small. And what's our result? Like, yes, you can obtain poly and polylog T bounds. So again, so up to polynomial factors, these are tight. And Bansal and Spencer had a result like last year, which obtained such a thing for independent coordinates. And at a high level, like how our techniques work is we still apply, you can say like Bansal Spencer kind of techniques, but the main thing is like their proofs break up for correlations. How we address it is by changing the basis. So what we show is that you can move to a new basis, so eigenbasis or Haar basis, some interesting basis, where in this new basis, the coordinates, the vectors that are arriving, they have this interesting property that expectation xi xj is 0 for I not equals 0, which we call uncorrelation. So this property becomes useful because although, I mean, in general, the proofs don't work in the original basis. When you use the potential, we combine it with some anti-concentration lemma, which is our main technical lemma, that for these uncorrelated random variables, we have some anti-concentration such that which ensures that the potential always remains bounded. So that's the main technique. And once the potential is bounded, the discrepancy also gets bounded. So just to conclude, like, yeah, we have all these results for vector balancing and Tosnadi's problem, d-dimensional, the main techniques. And so one thing I want to comment, like there are some recent, very, very recent follow-up works. So first, like we extended our techniques from this work along with Raghu Mehka to obtain square root as polylog bounds even for stochastic, vector balancing. Basically, this is improving these results like dependencies on n to s. And there's a very recent work like which got uploaded on arXiv just yesterday, which even obtains this result in the oblivious inverse. That's it.
Yeah, thank you very much for the nice talk. Do we have questions in the audience? Let's see. Okay. Yeah, so I don't see any questions. So thank you very much. And I think we move right away to the next talk. Yeah. So yes. Can you try to share the screen? Yeah, this looks great. Yes, we can hear you. We can see the screen. Everything's fine.
Okay, thank you.
Yeah, I guess we just start, right? So
Okay.
our next talk is on online primal dual meets online primal dual meets online matching with stochastic rewards, configuration LP to the rescue. And the paper is by CG Huang and Yan Kun Zhang. I hope this was correctly pronounced.
Okay. So I'm going to present online primal dual meets online matching with stochastic rewards, configuration LP to the rescuer. I'm Qiankun Zhang from the University of Hong Kong, and this is a joint work with Zhi Huang. So let me first introduce the model called online matching with stochastic rewards, which was first introduced by Mehta and Panigar in 2012. The model gives a bipartite graph G with vertices sets U and V and the edge set E. Vertices in U are known upfront to represent advertisers in the online advertising platform, and vertices in V arrives one by one to represent impressions. Each edge UV has a success probability PUV to describe the click-through rate. And when an online vertex V arrives, its adjacent edges and their successful probabilities are reviewed. And then we must match it to one of its neighbors irrevocably. And if V is matched to U, U will succeed with probability PUV. And if it fails, U is still available for the later online vertices. The objective is to maximize the number of successful offline vertices. So our research will focus on the validation probability case where PUV tends to 0, which has been the focal point in the previous research. So here is an instance with 4 offline vertices U1 to U4. When the first online vertex V1 arrives, it has 3 neighbors with success probabilities P1, P2, and P3. If V1 is matched to U3, and U3 will succeed with probability P2, and assume that U3 is not successful in this round, so that V2 can still be matched to U3, and then U3 will succeed with P4 in this round. Assume that U3 is successful, and when the next vertex V3 arrives, it has only one unsuccessful neighbor U4, and assume that U4 is successful in this round. So when the last vertex V4 arrives, because both of its neighbors have been successful, we must leave V4 unmatched. The total number of successful offline vertices in this instance is 2. Here are our results. For the equal probability case, we proved that the stochastic balance algorithm, which was also introduced by Mehta and Panigar, is 0.576 competitive and improved the best previous result of 0.567. And for the unequal probability case, we proposed a new randomized algorithm that is 0.572 competitive and improved the best previous result of 0.534. And as a last, our result can be generalized to the vertex weighting model. And then our analysis is based on the randomized primal dual framework, which was first introduced by Devanu, Kleinberg, and Jane in 2013. In the previous research using this framework, they all consider a standard matching LP as a benchmark. The standard LP takes a decision variable XUV on each edge, and accordingly, there is a dual constraint on each edge that need to be satisfied. However, we find that it fails to give any competitive ratio better than the trivial 0.5. So our solution is to use the configuration LP instead of the standard matching LP as a benchmark. Instead of taking variables on the edges, the configuration LP takes a decision variable XUS on each offline vertex U and the subset of its neighbor S to represent the probability that S is matched to U. The change of the decision variables lead to the change of the dual constraints, and this allows for an implicit amortization among vertices in S, such that it is easier to be satisfied than the standard matching LP. Okay, so that's all. Thank you.
Thank you very much. Are there questions in the audience? Yeah, so there's question here whether the competitive ratios are optimal, or are there any upper bounds for the model?
Okay. Optimal may not. Both of the optimal, both of the compare ratios are not set. And upper bounds, there is actually upper bounds introduced by the Mehta and Pangrahi in the Fox paper, and they show that the hardness result is, I do not remember the exact value, but it's slightly smaller than 1 minus 1 over E. And this shows that the model is strictly harder than the classical online bipattern matching model. Okay, thank you.
So there's another question: where are the major improvements using randomized primal dual comparing to the previous results?
Okay, maybe this may involve some technical details. And I think the major improvements is that for the equal probability case, we improved the alternating path argument in the previous paper. In our paper, we not only characterize the whether an offline vertex is matched to, or whether an online vertex is matched or not, but we try to capture the quality that an online vertex is matched to, and this can be measured by the unsuccessful attempts of the offline vertex.
Okay,
thank you.
More questions. What is known if the capacity of each U on the left has large capacity, say at least some value K?
Has the large capacity, that means that you can imagine that if an offline vertex has a very large capacity, that all of the its neighbor, including those in S, will match to it or match to a better offline vertex than it, such that this is actually a very good case, and it is not the bottleneck of the model.
Okay, and there's one more comment. Nice talk. Can you suggest some future directions?
The future directions, I think for the model itself, it is actually not clear for not clear to whether there is a tight algorithm, and we need to close the gap between the upper bound and the lower bound. And for the algorithm aspect, we may try to use the randomized Primal dual framework using the configuration LP in the matching problems. Okay, that's all.
Okay, thank you very much. Now
you.
Let's move to the next talk. Yeah. Okay, can you share the screen? Yes, okay, that's nice. Yeah, 1 second. So our next talk is on unbounded lower bound for K server against weak adversaries. And the paper is by Marcin Bienkowski, Jaroslav Birka, Christian Köster, and Lukas Jess.
Okay, thank you very much. So let's start by defining the K-server problem. So in this problem, we have a metric space, and there are K-servers which are located in this metric space. So here's a little example where there are 3 servers, so K is 3. And now points of the metric space will be requested one by one. And after a point is requested, we have to select one of the servers to move to this point. And after we've done this, the next point will be requested. And again, we have to select a server to move there, and so on. And we have to make these decisions without knowing the future requested points. And the goal is to minimize the total distance traveled by all the servers. And so just very briefly, it's known for deterministic algorithms that the competitive ratio is linear in K. And for randomized algorithms, there are upper and lower bounds, which are polylogarithmic. So in particular, in both cases, we know that when K is very large, then the competitive ratio is also very large. And this motivates to consider this problem in the resource augmentation setting. So this is also called the HK server problem. It's exactly the same problem as the K server problem. The only difference is that we define the competitive ratio a bit differently. So we compare ourselves to an offline algorithm that has only H servers instead of K servers. So the algorithm is row competitive if the cost of the online algorithm with K servers is at most row times the cost of the offline algorithm, where the offline has H servers, and yeah, maybe some constant, of course. And then I'm going to use the notation RxHK to denote the competitive ratio of the HK server problem on the metric space X. And for this problem, in the case when X is the uniform metric, so then it's also equivalent to the caching problem that we heard about in the first talk, or we heard about a variant of this problem. So in this case, it was shown by Slater and Tarjan in 85 that if K is only an arbitrarily small factor bigger than H, so if you only have a few more online than offline servers, then the competitive ratio drops down to a constant. And the main question in the setting is whether this is true for every metric space. So is it true that this competitive ratio of the HK server problem is a constant for every metric space X if K is only an arbitrarily small constant factor bigger than H? And of course, the competitive ratio would depend on this epsilon here. Or you can also ask a weaker question. So can we get a constant competitive ratio on every metric space if K is sufficiently large? So say K over H goes to infinity. And it has been shown for a couple of classes of metric spaces that the answer is yes. But in the general case, it has not been known whether the answer is yes. And there was also no metric space where there was a lower bound, therefore. So the only lower bounds we had before were all constant. And yeah, our contribution in our paper is to answer this question. And perhaps surprisingly, in light of the previous results, it turns out that the answer is no. So more precisely, we show that there exists a metric space where the competitive ratio of the HK server problem is at least log H. So it's not a constant, it grows with the number of offline servers. And this is no matter how big K is. And as a consequence, we also therefore get that for the so-called infinite server problem, that there is no finitely competitive algorithm for this problem. So this follows basically from our theorem and from earlier work. And let's briefly look at a crucial idea for the proof. So suppose that we have a lower bound of rho on the competitive ratio for some fixed ratio of K over H, so ratio of online to offline servers. And we're going to construct a tree now, and the goal is to show the same lower bound rho holds also for a larger ratio of K over H. And therefore, by repeating this step many times, we get the same lower bound rho for arbitrarily large ratios of K over H. So if the ratio is 1, then of course we can start with a very big rho, like with an arbitrarily big rho by just choosing K large enough. And so yeah, as I said, we're going to construct a tree, and this is going to happen recursively. So suppose that in these triangle subtrees at the bottom, we have this lower bound of rho for this fixed ratio of K over H. And now I'm using these purple bars here to indicate the number of online servers in these subtrees. So there are a lot of online servers here and only a few online servers here. And now we're going to start playing in some subtree that has no online servers. And we issue this request sequence for which we have the lower bound. So this is going to increase the number of online servers here, and therefore it's going to decrease the number of online servers in the other subtrees. And then we stop once we've reached a desired number of online servers. And now we're going to play in another subtree where we already have online servers. And we're also going to issue the request sequence for which we have a lower bound there. And we're going to keep doing this and always selecting the subtree with the fewest number of online servers here. And so this basically concludes a phase. So we know for this phase that in each of these 5 subtrees, we achieve this lower bound of rho. And also in each of these 5 subtrees, the ratio between online and offline servers is the one that we started with. And one can then also show that you can coordinate the offline servers so that along the top edges here, you also get this lower bound of rho. But now the crucial fact is that we have a few extra online servers here, and this therefore overall increases the ratio between the number of online and offline servers. So using this idea, we can add more and more layers to the tree, and eventually we can get the same lower bound rho, which is arbitrarily large for an arbitrarily large ratio of k over h. And yeah, so if you find this interesting, then check out the 25 minutes version of our talk, where basically we give a, well, almost complete proof, because it's really a very simple proof actually. And yeah, thank you, and I'm happy to take questions.
Thank you very much for your nice talk. Are there questions? Okay, so I don't see any questions. Yeah, then, oh, there's one question. The lower bounds are for randomized algorithms as well, right?
Yeah, that's correct. So the lower bounds hold for both deterministic and randomized algorithms.
Mm-hmm. Okay.
So if we have randomized algorithms, then the size of the bar basically represents the expected number of servers we have there. And in fact, thinking about randomized algorithms helped us to find this lower bound, which might be somewhat surprising because you would expect the deterministic lower bound to be bigger. Because we have basically this fractional view of groups of servers, it was easier to think in terms of these randomized algorithms.
Okay. Yeah, thank you very much. And let me also thank all the speakers again in this session. And yeah, I think this finishes our session. Thank you.